In this video, we're going to be discussing what it looks like to use a lot of different trig identities to represent trig functions. So in doing so, we'll be able to rewrite some trig functions in different ways and then simplify them. There is a resource page attached to the teacher website in Unit 6. Up at the top, you got this Laws and Identities resource page. That's a good thing to have handy when you're doing these. Print that out if you have the ability, or just open it up in a window so that you can refer to it often. Some of these identities you're familiar with already. For example, hopefully you're familiar with the fact that tangent can be represented as sine over cosine. Tangent is the ratio comparing the y-coordinate to the x-coordinate, and we get our y-coordinates from our sine function and our x-coordinates from our cosine function. So just another way to represent tangent there. Of course, the reciprocal of tangent, cotangent, would just be our ratio flipped here. Other reciprocal identities that I hope you're familiar with: if we flip sine, we get cosecant, so cosecant must be 1 over sine. If we flip cosine, we get secant, so secant is 1 over cosine. And then, like we just saw when we flip tangent, we get cotangent. Another way to represent it, rather than using these functions as a ratio, is just to say 1 over tangent. And then, of course, the reciprocal of what we just described right there. So those are hopefully some that you're already familiar with. In this video, we're going to be describing some Pythagorean identities, just different ways that we can represent the Pythagorean theorem using tangent, sine and cosine, secant and cosecant. There are some other identities, well, lots of other identities here. In the next unit, we'll get into our law of cosines and sines. So you don't really need that on this resource page. A lot of these other ones, like, we don't really have time this year to get into them. Some even and odd identities you may need for that assignment on My Open Math, but that's just pretty simple identities right there. The double angle and half angle are a little bit more complicated, but a lot of these are just plugging in or substituting values to evaluate. Some ones down here that, again, we won't get into, but all of these are what are known as your fundamental identities or laws. But we'll just focus in this unit on these top 3 right here and a little bit of those even odd identities. And then when we get into solving equations, we may start to use the double angle and half angle. All right, so let's get into it. In that reference sheet, we saw that quotient identity saying that tangent was sine over cosine. There's another way that we can rewrite these identities by using the reciprocal identities, and we'll get another ratio that represents tangent. We know that sine is the reciprocal of cosecant, so sine is 1 over cosecant. Cosine is the reciprocal of secant, so 1 over secant is cosine. So if I just change those identities right there and do a little division of fractions, so I'm multiplying by a reciprocal, that's going to put secant on top and cosecant on the bottom. So here's another ratio that represents tangent, another identity that we can rewrite tangent using. Cotangent, of course, would be the reciprocal of that, cosine over sine, or cosecant over secant. X in these functions is representing the input variable. I don't want you to confuse that with our x coordinate here necessarily. So another way that we can rewrite our trig functions is using just a different input variable. Sometimes we use that theta, which I hope we're used to at this point. So in this next example, we're going to rewrite our Pythagorean identity. We are hopefully familiar with a squared plus b squared equals c squared, given to us by a right triangle, c being the hypotenuse squared. If we change that into terms that we've been using recently in our trigonometry units, we're going to change that a value, for example, to be our x coordinate. The y value is coming from that b value. We're just changing that letter. And c is now going to be represented by r, or the radius of our unit circle. So now instead of a squared plus b squared equals c squared, we can re-represent that as x squared plus y squared equals r squared. And we know that we get our x coordinates from a cosine function. So x squared is going to be the same as cosine squared. And this is probably something new right here where we have a exponent on top of a trig function. I'll explain that here. Two different ways that we can represent using exponents with trig functions. Since typically we have a parenthesis around our input variable, then when we square our trig function, we actually need an extra set of parentheses. So in order to kind of simplify that, I think mathematicians decided to do this instead. They're just writing that exponent above the trig function, and that way we don't have to double up our parentheses. It's a little messy that way. So cosine squared would just be cosine times cosine. No different way of getting our exponents there. But typically when we write it with trig functions, we're going to write it with that exponent right next to the trig function. So x squared is our x coordinate squared, which is represented by cosine functions. Our y value, our height, our y coordinate, is given to us using sine functions. So y squared would be represented as sine squared. Our radius on our unit circle is always a unit of 1. So r is 1, so we got 1 squared. 1 squared is 1. And so now we have our Pythagorean theorem represented using trig functions. Cosine squared plus sine squared equals 1. And we can solve for each of these different terms if we wanted. For example, if I subtract sine squared from both sides, then I'll have cosine squared equals 1 minus sine squared. And if I square root both sides to get to that cosine, well then cosine would be the square root of 1 minus sine squared. And we're going to say the positive or minus, and that's going to be represented by whatever quadrant we are using an angle from. And we'll get into examples of how we can use that differently in a little bit. So over here on the left, we just have different ways to represent that Pythagorean theorem. And then on the right, we have two more identities that we can get to from this equation. For example, if I take this equation and I divide each of my terms by cosine squared, well, cosine squared divided by cosine squared is 1. Sine squared divided by cosine squared, that's just sine over cosine, which is tangent, but since they're squared, sine squared over cosine squared is going to be tangent squared. So there's our 1 plus tangent squared over here. And 1 divided by cosine squared, well, that's that reciprocal. 1 over cosine is secant, but 1 over cosine squared is going to be secant squared. So there's how we get this identity. And then we can do something similar here if we instead divide each of these terms by sine squared. Well, cosine squared divided by sine squared is going to be cotangent squared. Sine squared divided by sine squared is going to be 1. And 1 over sine squared is going to be cosecant squared. So again, just more identities, tons of different ways that we can interpret trig functions by just rewriting them with equivalent identities. Well, let's practice doing some of them. Here we're going to simplify some trig expressions. We're going to try and take something that is more complicated and simplify it down to just a single trig function. So in order to do that, we're going to use those identities from that reference sheet. Hopefully at each step I'll be telling you which identity I'm using to get to my next step. In doing these, at first, man, it's really tricky. It's just one of those things that when you do it the first time, it seems weird. And it doesn't seem like really there's any rhyme or reason to it. And you're kind of right, like it is kind of a trial and error method at the beginning while you're doing it until you just get used to recognizing which identities probably work the best to get you where you need to go. So that's just going to take a little bit of practice and some trial and error before you get used to it. And then eventually you'll be able to choose the right ones based on your experience. All right, so here we got a basic one here where we're just going to factor to simplify. So because both of these terms here have a sine function, we're going to factor out sine. And so if I factor sine from here, I'm left with cosine squared. And here, if I factor or divide by sine, I get negative 1. Well, cosine squared minus 1 is pretty close to our Pythagorean identity here. If I had 1 minus cosine squared, that would be equal to sine squared. But here I have cosine squared minus 1. I have a negative 1 and a positive cosine, so that's not quite the same. So what we could do is we could just make everything the opposite to get us there. Or another way of thinking about it is to factor negative 1 out, or divide everything by negative 1, or multiply by negative 1. It all gives us the same result here. So if I make everything the opposite, this is negative sine of x, this is now negative cosine squared, and this is now positive 1. So now I have 1 minus cosine squared. I have that identity to give me sine squared. So I'm going to use my Pythagorean identity to just rewrite this as sine squared. In front, we have that multiplier negative sine times sine squared. Well, if I have a degree of 1 multiplied by a degree of 2, well, that's a degree of 3. So sine times sine squared is sine cubed, and a negative times a positive is negative. So we got negative sine cubed is the simplified form of this. All right, again, we just got to do a bunch of these. Once you see a lot of examples, you start to see some patterns that happen a lot. And then you can recognize, hopefully, those patterns and then be able to use what's necessary. So hang with me. We're just going to do a bunch of these. All right, here we have 2 terms, and again, they both have a common term. They both have secant, so we're going to factor secant out. If I factor secant out from this term, I'm left with sine squared. Factor secant out from there, I'm left with negative 1. Again, I have negative 1 and a positive sine squared. That's not exactly what I need for my Pythagorean identity. So we're just going to use that trick that we just used. We're going to factor negative 1, or just make everything the opposite. So now we have negative secant, negative sine squared, and positive 1. Now I have that positive 1 and that negative sine squared coming from my identity here, so I know that that's equal to cosine squared. If I just back up a step. So rewriting this as cosine squared, and rewriting this, I'm going to use my reciprocal identity. I can represent secant differently if I say it's 1 over cosine, because it's negative, I'm going to keep it negative. So now I have 1 over cosine times cosine squared, where here we're just going to simplify our fractions. We know that a degree of 2 divided by a degree of 1 is just going to leave us with a degree of 1, right? So cosine squared divided by cosine is cosine. And, oops, I probably should have made it negative. I'm sorry about that. That should be negative cosine of x. So that would be equivalent to this more complicated version of the same thing. All right, on to the next example here. See if you can maybe pause it and do a first step. Try and rewrite anything that you see using either those quotient properties or reciprocal properties. Well, sine, we're not going to rewrite. In general, this is a tip that I'll give you in the next video as well. In general, if you're ever stuck, try and get things in terms of sine and cosine. So here we have cotangent. I'm going to rewrite that in terms of sine and cosine. I know that using my quotient property, or quotient identity, cotangent can be represented with cosine over sine. Otherwise, I'm leaving everything else the same from there. Now I have this product right here. I have cotangent times cosine, but instead I'm doing cosine over sine times cosine. Cosines on top are going to get multiplied to give me a square, so cosine squared, and we're still on top of sine, and we still are adding this sign at the front. So all I did at this next step is just multiply my fractions here. But if you can see here, we are getting close to our Pythagorean identity. We have sine plus cosine squared. If I had sine squared here, well, then I could use that. Well, if we're going to add fractions, we know we need a common denominator. So if I give this term a denominator of sine, I got to multiply top and bottom by sine to make it equivalent. So I'm going to get sine squared on top of sine. If I simplify that, I get back to sine. So now I have a common denominator here with these two fractions. Oops, dang, another typo right there. I don't have cosine squared. That's supposed to be squared. Now I can add my numerators here and leave it over the denominator. So I have sine squared plus cosine squared. That's our Pythagorean identity. We know that cosine squared plus sine squared is equal to 1. So I can rewrite this entire numerator to just be 1 using that Pythagorean identity. So now I have 1 over the sine. And that's just a reciprocal identity that I can rewrite as cosecant. Another thing that's a little different in this is that our input variable is now t. So lots of different input variables that hopefully are not tripping you up. We can use theta, we can use an x variable, we can use any letter here as a variable, but typically you'll see x or you'll see theta. But just know that it could really be any variable. You're allowed to use any letter in the alphabet. All right, let's do another one. Again, try and pause the video and try and rewrite something if you recognize that you can rewrite it as something. For example, cosecant here. I know I can rewrite that using a reciprocal. So cosecant is going to be 1 over sine. I have cosine here. I'm going to keep it as cosine. But I'm going to rewrite my cotangent using that quotient identity. Cotangent is the same as cosine over sine. Now I have two fractions being multiplied, so I'm going to multiply those. I got cosine squared all over sine of x. And so if I have the same denominator here, well then I'm going to say that's 1 minus cosine squared over sine of x. And now we have this Pythagorean identity, 1 minus cosine. If I take my cosine here and I subtract it from both sides, then 1 minus cosine is going to be equal to sine squared. And so I can use that Pythagorean identity to rewrite this numerator as sine squared. So now I have sine squared divided by sine, and that's just going to leave 1 sine. So again, you see, using those common denominators, using the Pythagorean identity, the quotient identity, this is going to happen over and over and over again. There's one more trick that I want to show you in this video, and it's using the conjugate, or using a difference of squares to help us simplify. This is probably one of the trickier steps, but after you've seen it done before, anytime you see a fraction in this form, think about using this, this strategy or technique here. So multiplying by a conjugate is going to help me simplify because I'm going to be multiplying by a difference of squares. And anytime I do that, I get a simpler version of my two binomials here, just giving me a difference of two squares. As long as I multiply the top and bottom of a fraction by the exact same thing, well then I'm not changing the value, I'm just changing the way it looks. So this is the same as multiplying by 1, which is not going to change any value associated with this. So I'm allowed to do this, multiply by 1, but just in a crazy looking form here. I know I'm using 1 minus sine of x because that's the conjugate. Remember, conjugates are the same terms, just with a different sign between them. So on top, if I multiply, well, multiplying by 1, I just get 1 minus sine of x. On the bottom, though, I have 1 times 1, which is 1. I have negative sine of x plus sine of x. Those middle terms are going to cancel. And then my last product here is sine times negative sine is going to give me negative sine squared. And so down here now, hopefully you're starting to recognize your Pythagorean identity. 1 minus sine squared is going to be cosine squared. So I just rewrite the bottom using that Pythagorean identity. Now I have two numerator terms here. If I separate my fraction here and give each of those numerator terms their own denominator, so 1 over cosine squared minus sine over cosine squared, and then I just separate my cosine squared into 1 over cosine. So if we work backwards here, sine times 1 is sine, And cosine times cosine is cosine squared, so I still have that sine over cosine squared term there. But I've broken it up because sine over cosine is my tangent identity. And 1 over cosine is going to be my secant identity. And 1 over cosine squared is going to be my secant squared identity. So there we're using our reciprocal identity for that first term. We're using that quotient identity for that second term. And for the third term, again, we're using the reciprocal identity. So secant squared minus tangent times secant is the exact same thing as this. It's just no longer in fractional form. All right, you got one more there to kind of practice that technique of using the conjugate. Go ahead and pause the video if you need to and try and work it out on your own first. All right, here we're looking at the denominator. I see 1 minus sign. Its conjugate would be 1 plus sign. If I multiply top and bottom by the conjugate. On top, I could distribute, but that's not going to help me simplify. Remember, distributing is actually the opposite of simplifying, is expanding. So I want to keep it in this product form. Don't want to distribute, and I'm going to show you why on the next step. The bottom, though, we got that difference of squares. So we know that its product is going to be 1 minus sine squared. There's our Pythagorean identity. That's equal to cosine squared. So rewrite the denominator using the Pythagorean identity. And then here you can see why I didn't want to distribute, because now I can cancel my cosine squareds, and I'm just left with 1 plus sine. So again, exact same thing as this, just not in fractional form. All right, so there's a lot of practice right there using identities. You also have an assignment on the teacher website that helps you practice more of the same. And in the next video, we're going to just continue to practice that stuff. It's going to be called Verifying Trig Identities. It's actually a little bit easier, and it's the exact same skills. So keep watching for that next video to keep practicing using those identities. The other skill I want to talk about in this video is doing something that we've already done before. We're going to solve for the value of some trig functions, all 6 of our basic trig functions. But we're going to use identities this time to do it. It's not that you can't set up your right triangle in the quadrant like we did before and solve for that missing third side, and then use your knowledge of your trig ratios to write all these. That's perfectly capable method, but we're just going to do it slightly different and use identities to get the exact same values. All right, so same problem we've seen before. Given one of our trig ratios and some knowledge about maybe what quadrant we're lying in, we're going to be able to set up the other 5 ratios that we weren't given. All right, so remember that secant is comparing hypotenuse to adjacent. And knowing that I'm in a quadrant where tangent is positive, that happens in quadrant 3. I'm going to draw my right triangle in quadrant 3. And I'm going to label my hypotenuse 3. Remember, the hypotenuse can't be the negative value. And my adjacent side, so my x-coordinate length here, is -2. And we know that's negative because we're on the left side of the origin on the x-axis. We're in the negative version of the number line here. So there's where our negative is coming from. We also know in this quadrant that our y value here, the side length here, is going to be negative as well because we are below the origin on our y-axis, giving us negative values. But instead of using Pythagorean theorem in the way that we're used to solve this side, we're going to use identities to get our other ratios. So we're given secant. We can just fill that one in, -3/2. I know if I flip that, the reciprocal is going to be cosine. So cosine is -2/3. Because I know cosine, I'm actually going to use my Pythagorean formula, just in terms of trig here, to solve for my sine ratio. So watch what happens here. If we set this up to solve for sine, we're going to subtract cosine from both sides, cosine squared from both sides. And then we're going to square root both sides to get rid of that square. So our sine ratio is going to be whatever we get out of here, we know our cosine squared is our cosine ratio squared. So if I take my cosine ratio -2/3 and I square it, well then I'm going to square the top and the bottom. I'm going to get +4/9. In order to subtract that from 1, I need a common denominator. So instead of 1, I'm going to say 9/9. I'm going to do my subtraction. 9/9 minus 4/9 is 5/9. The reason why I'm going to use the negative version for my answer is, again, because I'm in that third quadrant where my sign ratio or sign value is going to be negative. So that's how I choose which positive or negative form of my answer that I want. I need to know what quadrant I'm in. So we make it negative whatever the square root of 5/9 is. To square root a fraction, I can square root the top and the bottom. I can only simplify the square root of 9 on the bottom to get 3, and I'm going to leave the square root of 5 in radical form. I'm going to keep that value negative, again, because I'm in the third quadrant where our sign value is negative. So now there's my sign ratio, negative square root of 5/3. And if I flip that, make it the reciprocal and rationalize, well then I'll get this form for cosecant, just the reciprocal of my sign ratio. And to get tangent, we're going to use one more identity. Remember our quotient identity. Now that we know sine and cosine, we can represent tangent in that ratio, sine divided by cosine. I can plug in my sine ratio on top and my cosine ratio on the bottom, and I can divide my fractions by multiplying by the reciprocal. My 3's are going to cancel, and I got a negative times a negative, which is a positive. So negative square root of 5/2 is my tangent ratio. And if I flip that and rationalize, then I'll get my ratio for cotangent. So there's how we could use those identities, the Pythagorean identity and the quotient identity specifically. You could have, however, used the Pythagorean theorem like we were used to. To find the side, it would be 3 squared minus -2 squared. That would be 9 minus 4, which is 5, and the square root of 5 would be that side length. And then I could say, well, sine is opposite over hypotenuse. Well, we just said that. We make sure that that's negative because we're in the third quadrant. Our tangent ratio would be opposite over adjacent. So negative square root of 5/-2 would be the positive version of that. So you can see that it works out the same as what we've done before. Again, this is just a different strategy, instead using identities to do it. You got one more here that you can use to practice, and you can check your answers when you're done by pausing the video. All right, plenty to practice there. Mostly, I just want you looking at those identities and getting used to rewriting things that you see using different identities. Again, to get started, it's more of a guess and check method, and you'll get more and more used to it as you do it again. We'll continue to practice in the next video as well, so check that one out.